Okay, this is our next installment of Pandemic Theater, Chemistry and Light. What we talked about last time was understanding what determines the energy of the Bohr atom. Remember that we talked about the Bohr model. We derived what the energy of the energy levels of the Bohr model were. Let me remind you what they were. We found that the energy levels of the Bohr atom were quantized, which means the electron in the atom could not have any possible energy, but it was restricted to a specific set of energy levels separated from each other by specific differences. Now, we didn't say that there was a, and so we mentioned that the energy levels of the Bohr atom were labeled by the quantum number n. And n started at 1, and then increasing numbers by 1. It kept going and going and going. We didn't say where it went, but we also didn't say there was a restriction on it. And so we expect that n can go all the way from 1 to infinity. Generally speaking, we're all consistent with the Bohr model that we described. We plotted the energy in terms of it going up, increasing upwards, and noted that the energy level difference here with this arrow between the first and the second energy level is large, then smaller between the next two, smaller still between the next two, and smaller, and so the energy levels are getting closer and closer together. Okay, so this is where we left off. We also talked about that when the electron occupies any one of these energy levels, or we say that it is moving in a specific Bohr orbit, where the distance that the electron is away from the nucleus depends on this quantum number n. And we derived an expression exactly how it depends on the quantum number n. But for now, what I want to continue talking about is the idea of light absorption by the atom. And the Bohr atom provides the simplest possible model within which one can understand light absorption. Once one acknowledges the fact that light is made up of photons, photons are particles, quanta of light, or packets of energy, and that packet of energy, that quantum of light, is indivisible. If a photon has a specific energy, you cannot take it and split it into two parts. So if something absorbs that light, it must absorb all of it at once. You may try to think about all sorts of other complicated consequences when a photon can be split into more than one part, but we take the photon to be an indivisible unit. And that you can't have a little bit of the photon left over. Now, there are mechanisms, if one studies quantum mechanics further, where a single photon going through a specific optical element can give rise to two photons coming out, two or more. We're not going to think about that case. That requires very specific circumstances. And so, for our purpose, if a photon of light is absorbed by an atom or a molecule, the entirety of the energy of that photon is absorbed, not some fraction of it, but the entirety. Well, what that means is because the energy levels of the Bohr atom are quantized, and the photon comes with a single packet of energy, all of which must be absorbed. But these are the possible energies of the electrons in an atom, so there is no energy in between here. That doesn't exist. And so the frequencies of light, the energies of photons that an atom can absorb are very specific, because the photon is absorbed as a single particle indivisibly all at once, but the electron can only make jumps from one energy level to the next in absorbing that photon in specific units. And so this energy, from this value beginning to this fictitious energy, there is a frequency of light that would correspond to absorption into this energy, but there is no energy level here. The Bohr atom says that the electron can only have these specific energy levels and nothing in between, right? That's the consequence of being quantized. And so the frequencies of light that the Bohr atom can absorb are going to be ones that meet this energy condition. I absorb this photon entirely, but I'm only able to jump between these specific energy levels. What does this mean? The condition that this implies is that the difference, delta E, between any two energy levels, let's say from some n to n prime, where n is the initial quantum number, and n prime is some final quantum number. This energy difference, that is to say, when the electron absorbs energy from somewhere and goes from this energy level labeled by n, for example, n equals 1, to some other energy level, n prime, for example, n equals 3. This energy difference, if this energy is supplied by virtue of light, must be exactly equal to the energy of the photon. Photon energy. This is nothing more than energy conservation. If a photon carries this amount of energy, and all of it is imparted or transferred to the atom via absorption, then all of that energy must go into exciting this electron up to some other energy level, such that the only frequencies of light that can be absorbed are ones that coincide with some specific energy differences, and not anywhere in between. And so the types of frequencies of light that an electron can absorb within an atom are very specific to that atom. Let's take this a little bit further. What is delta E as an electron goes from n to n prime? Well, let us remind ourselves that we said that the energy of the electron in the atom looks like minus 13.6 electron volts times z squared over n squared, where z is the charge in the nucleus. If it's hydrogen, it's plus 1. If it's helium, it's plus 2. N is the quantum number. One thing that we didn't say, but we should say explicitly now, is that this formula applies only to atoms that have a single electron. Yes, we didn't restrict ourselves to a specific nuclear charge or atomic number, Z, but we are explicitly restricting ourselves to atoms that have only a single electron. And so it's most naturally applied to the hydrogen atom, where Z is 1. But if you have a helium atom that is missing 1 electron, that's also fine, right? A helium atom has 2 electrons and 2 protons. But when helium becomes ionized and becomes helium plus, it's 2 protons and 1 electron. And so a helium plus ion will behave energy level wise the same as a hydrogen atom. And so this formula applies to any hydrogenic atom, is what one says. A hydrogenic atom is any atom that has any number of protons and neutrons and only 1 electron. For example, carbon has 6 electrons. If you ionize a carbon atom 5 times and make a C5 plus ion, it will be a hydrogenic atom, and therefore will have an energy level structure that looks exactly like this, with a Z now of 5 as opposed to 1. So this is the energy level, the value of the energy level when the quantum number is some n. Now our task is to find the energy level differences when the electron goes from some initial level n to some final level n prime. And that will determine the frequency of light that can be absorbed, because the two have to be equal. And so let's write this down. After the electron absorbs light, or this photon of energy, it will be an energy level En prime, but it started off in energy level En. So En prime minus En is delta E, this energy difference. This should equal h nu. Well, what is En prime minus En? This is minus 13.6. Oops. I'm going to stop writing EV, so we have to remember that we're measuring our energies in this unit of electron volts. Z squared over N prime squared, close parentheses, minus Z squared over N squared. And if we rewrite this, let's now erase here too. If we rewrite this, we find that delta E, or En prime minus En, equals minus 13.6 z squared 1 over n prime squared minus 1 over n squared. And this equals h nu. What does this mean? This means that the atom will absorb many possible frequencies of light. Not just any particular frequency, but any possible frequency of light. The atom is capable of absorbing, in principle, any frequency of light. Let's make this explicit. Photon frequency, where h is Planck's constant. And remember, this is also equal to hc over the wavelength, because the product of the frequency and the wavelength has to be equal to the speed of light. And so you can always express the frequency or the wavelength in terms of each other by using the speed of light. And so the atom will absorb a number of different frequencies or a number of different wavelengths of light, or photons, each of which corresponds to some transition from some initial quantum number n to some final quantum number n prime. By the way, let's make certain of something. We see this minus 13.6 over here. By the way, let's make this explicit. In units of electron volts. Make this clear. The photon energy has to be positive. Always. If it's being absorbed, the photon is going to deliver this amount of energy into the atom. If the atom absorbs this amount of energy, it should increase the energy that it had before. And so the final energy should be higher than the initial energy. Let's make sure this is true. Is this delta E actually a positive number? Well, n prime is going to be larger than n, right? For example, this might be 1, this might be 4. So if n prime is larger than n, 1 over n prime squared is smaller than 1 over n squared. If this is smaller than that, this difference is going to be a negative number. Negative number multiplied by the negative gives you a positive, and so the world is not upside down. Everything is as we would expect. And so let's make this point clear, is that the atom is capable in principle of absorbing many possible frequency of light. Not every possible frequency of light, but very specific frequencies of light. Nevertheless, there are many of them. Frequencies of light or wavelengths of light. The set of all possible frequencies of light and or wavelengths of light is called the absorption spectrum of the atom. So what is the lowest frequency of light that the atom might absorb? Well, the lowest frequency should correspond to the smallest possible difference. The smallest possible difference should be when these numbers are closest to each other. When would these numbers be closest to each other? Something to think about. For example, what kind of situations might we imagine? These are the energy levels, and we noted that they're getting closer and closer together. If we can assume that the electron starts with n equals 1, then the lowest possible energy, and therefore the lowest possible frequency of light, should correspond to n equals 1 to n equals 2 transition. The next highest energy should go to n equals 2. The next highest energy should go to n equals 3. And so this will be some frequency of light, call it n12. This will be some frequency of light, call it nu13. This is nu 1,4, and the frequency is getting progressively larger. As the frequency is getting progressively larger, the wavelength is getting progressively smaller. And so, if we can assume that the atom is going to be found in the first energy level, we might draw an absorption spectrum where this is the frequency of light. This is some 0. Let's say this is a scale break frequency in units of 1 per second. And somewhere here will be the first frequency that it will absorb, assuming it starts at n equals 1. This is nu 1, 2. Someone here will be nu 1, 3. Here, nu 1, 4. What I mean by 1, 2 is that n equals 1 for the beginning, n equals 2 at the end. So the electron goes from one orbit to the next, in this case from the first orbit with n equals 1 to the second orbit with n equals 2. And of course, when we turn on quantum mechanics, we would speak of the orbital with that quantum number. But the energy level idea is, of course, identical. What we'll later on discuss is the, by the way, I should label this axis. We were going to call this axis absorption. And we haven't said what absorption is, but we will at some point. And we might draw a line over here, a vertical line, where this labels, the x-axis labels the frequency of light that is absorbed, and the y-axis labels the absorption magnitude. How much does the atom absorb? And that's not something, how much is not something our model is able to answer in this case. One needs to go a bit further. But identifying the frequencies of light, which colors is the atom going to absorb and which is it not going to absorb? Well, we're saying that these frequencies, the atom, and many others, the atom will absorb. The frequencies of light in between, perfectly fine photons, will be completely transparent with respect to the atom. They will simply fly by the atom. There will be zero probability that they're absorbed. No matter how many times the photon flies by the atom, it will never be absorbed if its frequency is somewhere in these gaps. But if this frequency is here, what we find is that there is a probability that the atom absorbs that photon. Not every single one, but every once in a while it will absorb that photon as it flies by it. And so this is the very basics of light absorption with the Bohr atom. But the idea of an absorption spectrum, which identifies the specific frequencies or wavelengths of light that the atom can absorb by virtue of all of these possible transitions, the electron jumping from one quantum number or one orbit, smaller to larger, as it absorbs these photons. Now, something interesting should also be thought about. Let me now erase this. Remember that we said that when an electron in an atom absorbs light, it necessarily hops from one what's called allowed energy level to another allowed energy level, but and not anywhere in between. And therefore only very specific frequencies of light can be absorbed. But the way the electron gets from n equals 1, for example, to n equals 2 or any other quantum number does not necessitate that only a single photon is absorbed. And so there's this idea of multi-photon absorption. And the simplest manifestation of that is what's called two-photon absorption. So, two-photon absorption. The idea behind two-photon absorption is that Let's start with a simple example of a transition of an electron from n equals 1 to n equals 2. It's possible that two photons can be absorbed simultaneously, satisfy the conservation of energy principle, and allow the electron, by absorbing two photons of some intermediate energy, to hop from n equals 1 to n equals 2. And of course, once again, we see that if it's absorption of two photons that are identical, then the energy of the photon has to be exactly half the energy difference between n equals 1 and n equals 2. And so we would say that delta E n to n prime is equal to 2 h nu. This is a statement of energy conservation. And this doesn't violate any of the principles that we said. The photons are still getting absorbed as a single packet of energy. It's just that two of them are getting absorbed simultaneously in making the electron undergo this transition from n equals 1 and n equals 2. And so this does happen in practice. The point that we made earlier is that the idea of a photon getting absorbed is never guaranteed as the photon is flying by the atom. There's a probability of it, and quantum mechanics allows you to calculate that probability. There is an even much smaller probability that the electron can absorb two photons at the same time. Usually that requires a very powerful laser. But nevertheless, there's actually really interesting reasons why one may want to use two photon absorption for medical applications, particularly penetrating skin with light. Okay, so that's two photon absorption, and of course you can imagine three photon absorption. The issue is that by the time you get to three or more, the probability of the electron absorbing them simultaneously, three photons at the same time to make a jump like this, is near zero, so it can be completely discounted. So two photon absorption is really the only multi-photon absorption step in this kind of a scenario that one needs to worry about. Okay. The last thing that I want to do in this very coarse introduction to light absorption by a Bohr atom is the idea of ionization of the electron in a Bohr atom. And so an obvious question that may come up is how much energy does it take to ionize a Bohr atom, i.e. take the electron and completely remove it out to infinity? And if you can answer the question of how much energy does it take, well, what frequency of light or what wavelength of light would that correspond to if an electron in a Bohr atom absorbed all of that light energy and in so doing got kicked out of the atom? To do this, I want to remind ourselves of something. Remember the electric potential energy that we had to deal with when we discussed the Bohr atom. What we found is that, or what we discussed is that the electric potential energy between a proton and an electron, some distance r apart, this electric potential energy look like minus 1 over 4 pi epsilon naught z e squared over the distance r. And if you plot this potential energy as a function of r, you would get a curve that looks like this. And this is 0. And the potential energy is negative when r becomes small. Right? When r is very large, when r is infinite, so when the electron and the proton are very, very far apart, the potential energy goes to 0 according to this formula. And so it asymptotically approaches 0 as r goes to infinity. As r goes smaller and smaller, the potential energy goes down from 0, so it becomes more negative. We may actually draw the hydrogen energy levels something like this. Suppose this is E1, suppose this is E2, 3, where 1 is quantum number n equals 1, n equals 2, n equals 3, 4, 5, 6. And they should get closer and closer together. In fact, they should get so close together so as to become completely dense, nearly continuous, eventually. In fact, we can kind of do a fun thing. We can go towards this energy and then go upwards and say this is the first Bohr orbit, something like this. This is the second Bohr orbit. So the electron is here away from the proton when it is in E equals 1 with quantum number n equals 1. When it's in quantum number n equals 2, this is where the Bohr orbit is, so it's getting farther and farther from the proton. R3 and so on. And as r goes to infinity, of course, you see that you approach 0. So the zero of energy is an arbitrary thing. You can set the zero of energy anywhere you want, just like you can measure height from any point that you want. So when we measure height on Earth, we oftentimes measure it with respect to sea level. We've set the 0 there. Here, we've set the 0 to when the electron and the proton are infinitely far away. We could have added some constant to this point and then made that not be the case. But in any problem where it is the difference in energies that is important, that constant would cancel, and so it doesn't matter. And so it's a natural choice to set the 0 of energy when r goes to infinity. But for our perspective, we see that as the electron is going farther and farther away from the nucleus, and that's what we mean by ionization, right? We separate the distance between the electron and the proton to infinity so that they're no longer associated with each other. The atom has been ionized. You see that this corresponds to n, the quantum number, going to infinity as well. What is the ionization energy? It is the total energy it takes to take the electron that was in the lowest energy level, E1, all the way out to infinity. So you ionize it. But that corresponds to giving the electron energy from E equals 1 to E sub infinity. So the ionization energy, sometimes called the work function, if it's not an atom you're discussing, but a material, like a solid of some kind, like zinc solid, copper solid, silicon solid, whatever. Ionization energy, let's call it IE, should be equal to delta E from n equals 1 to n equals infinity, which corresponds to infinite separation between the electron and the proton, and the energy going to 0. And so this is equal to minus 13.6 electron volts. If it's the hydrogen atom, let's take this for specifically hydrogen atom, i.e. Z equals 1, this should look like 1 over n prime squared. I'm sorry, now we're going to put in our actual n's. Infinity squared minus 1 divided by 1 squared. And this equals 13.6 electron volts. And so the ionization energy of hydrogen is 13.6 electron volts. And so it takes a photon of this much energy with a frequency corresponding to that energy, or a wavelength corresponding to that energy, to liberate an electron from a hydrogen atom, i.e. move it from the energy where it's in its lowest energy level, E equals 1, all the way out to infinity where the potential energy is 0. And in this case, the total energy is 0 because of the relationship that we derived for the hydrogen atom before. Okay, I think that is sufficient for now, and let's end there.